So I stopped the last video prematurely, but it's actually a pretty decent place to stop. Note what we did here. We used this particular formula, and we used it to get to velocity. And what we would like to do is actually use all this stuff about the work, because if we don't make any use of defining the work and using it, then what's the point? All right, so I'm going to go back to this slip of paper here. All right, you remember this? We're going to take and look at this formula. V final squared is V initial squared plus 2a delta x. And I'm going to multiply by, oddly enough, I'm going to take this whole thing and multiply by m over 2. So what we'll have is m v final squared over 2 equals m v initial squared over 2 plus ma delta x. And in this bit, I'm going to isolate. So we'll have ma times delta x is m v final squared over 2 minus m v initial squared over 2. And the thing in the parentheses here is the net force and the displacement. And this is where we get to a little trick, is when we talked about this, it really is the acceleration vector dotted with the displacement vector. And all these squareds, v squared is really vector v dotted with vector v. So here there really is a sum of the forces dotted with delta x, which is what we call the net work. This over here we haven't defined, and so let's define it. The kinetic energy K is going to be 1/2 mv squared. So this is how the kinetic energy changes. It starts at some initial value, K initial, and we'll have K final. Well, that's just delta K. So the net work equals the change in the kinetic energy. So that's what we call in the notes the work kinetic energy theorem. Is we're saying that in order to find, say in the problem that we worked on before, to find this velocity that we used, right, where we were trying to solve a kid sledding down a slope, or trying to find the velocity at the end, we can use the work, and by taking the net work, we can use it to find this change in the velocity through the change in kinetic energy. So let's try that. All right. What we note here is that our weight force does 5,000 joules of work. Our friction force does 300 joules of force. So our normal force does no work. So the net is 4,700 joules. So we can use that in. Right. Our initial kinetic energy is 0 because V initial was 0. Right. We started the sled at the top of the hill from rest. So, our velocity is 0. And we can use that to find what K final is, because this net work is the change in the kinetic energy, which is K final minus K initial. So it is Just so you know, if you hear it in the background, my parents are watching Gunsmoke, and it's the same one they've seen at least 8 times this semester. So, um, we can solve for V final. V final is 2 times 4,700 joules over 50 kilograms. And now we grab the calculator. 2 times 4,700 divided by 50, square root 13.7 meters per second. And it works. So, you might be thinking, well, why do I bother to do this? All right. I mean, don't I have a perfectly reasonable idea of going through finding this stuff, finding the forces, and finding the acceleration and finding the velocity? In this problem, yeah, you do. Let me pause on a new sheet of paper. We're going to start with the same sort of setup. What if the sled fell off that way instead? So just a straight free fall problem. Then delta x is 10 meters from our sketch. I'll put the sketch over here off to the side so you can see it. And V initial is 0, and A now is 9.8 meters per second squared. And V final is what we're looking for. And so from this, we would get, I'm going to call this delta x h for reasons eventually, because we called it here, h is 10 meters. So V final squared is V initial squared plus 2a delta x, which is V is square root of 2gh. So we can plug that in. 2 times 9.8 meters per second squared times 10 meters. We'll take the square root. 2 times 9.8 times 10. We take a square root. And that is 14 meters per second. All right, so that's okay, that's fine. Now we let the kid go down the ramp this way, and first we'll say it's frictionless. Well, going down the ramp this way, you have a normal force and a weight force, and the part that makes it go down the ramp is the weight times sine theta. But that's the bit that's the mass times acceleration. So our acceleration is g sine theta. So we can look at it in terms of this problem. We still know the same things. To get to the bottom of this ramp, now let's say theta is 30 degrees. So delta x is h over sine 30 degrees is 20 meters. The initial is 0. A is 9.8 meters per second squared. Sine of 30 degrees is 4.9 meters per second squared. And V final is what we want. And we do the same math. What we'll get is V squared, or V final squared, is, well, V initial squared is 0. We'll get 2 times, writing it out in terms of the way I've written it out here, g sine theta h over sine theta. Or we get that V is square root 2gh. So without friction, we get the same answer. There's something fundamental about this equation, and you've seen it before. It literally is the work kinetic energy function theorem. It's the same thing. We're just ignoring that. But what the work kinetic energy friction lets you do is solve for when there's friction in the problem, or solve for when you don't know what's going on. What if instead of all of this, we had something that was a loop-de-loop? How would we ever figure out a geometry for that? We would have to throw it at a computer and let it do the complex integrals that we were doing. We don't want to do that. We want to do the easy stuff. So briefly, by the end of this, we're going to define one more thing because there's something fundamentally interesting in here, right? What's happening here is we're letting gravity do some work, and we can look at the work that gravity does. So we'll do the work that the weight force does, and it'll turn out that no matter what the geometry of the problem is, right, the weight force is always going to be down. So no matter what the displacement is, we can just put in one in here, whatever it is. We'll call this delta x, but we'll call this component of delta x h. All right, so if this is our delta x, there's our right triangle, this is h. That's going to be with, there's an angle here I'll call alpha, and an angle here that'll be theta. Right? So alpha plus theta is 90 degrees. That means this is theta. So when we write this out, this is going to be the weight force times delta x times cosine theta. But delta x cosine theta is h, which is the weight force times h, which is mgh. Is there anything else? So we're being careful in defining stuff. H here, we got to be careful of, because it's not really H, it's H initial, H final. Right? It's between those 2 points. So the way we define things, we want to be very careful how we're trying to define what's going on here. Right? Our delta x is always defined as final minus initial. So we would have h final minus h initial in a sense. But I don't know how to express this. It's kind of weird. Anyway, the point is, this is a fundamental sort of thing, and it's what we call a conservative force, which is that all that matters is its height. It matters the vertical the distance along the weight force. It doesn't matter if my actual path for this object was more like that. Right? If it's the red line, say I threw a ball up in the air and it fell down to this point, I should get the same effect as if I just allowed it to go there, or if it rolled down this ramp. The idea is, as long as the forces acting at are the same, and the initial conditions are the same, I should get the same outcome. So this is kind of a fundamental thing. This is why we define the potential energy. So we'll also define this as U. You'll see that in your textbook. And this is going to be mgh. So what I'm trying to get at here is, when we start talking about potential energy, the work that gravity does is defined as minus the change in potential energy, which is mg h final minus mg H initial. So we're being very, very careful how we define these things. Now, I'm going to show you an example of actually using it. We don't often have to worry about exactly where all these minus signs come in. We're just trying to solve problems. So let's stop the video there, and then we'll do an example and come back to it.